Introductory notes. So let's talk a little bit about the introductory cause and effect behaviors in injection molding. That is one of the most important things you can learn, is not necessarily only part design or only mold design or only processing. No, you have to really understand the interactive behavior in injection molding, what we call the cause and effect behavior in injection molding. So that's really an important aspect of learning, is the interactive behavior in injection molding. Okay, so let's get started. So what we will do in this seminar, in this webinar, is cause and effect behavior of injection molding, which just give you a quick overview of what we talk about when we talk about cause and effect behavior. We'll talk a little bit about our Circle of Knowledge online training program. I just want to outline very briefly what we are doing here. We will look at the Polymer Materials Overview. This is really our cause and our from the webinar. Yeah, that is our lesson for today. And at the end, we have a little bit of a Q&A. And if you are interested in posting a question, please use your chat function in your GoToMeeting invitation to send us a question during the webinar. You can type it in, and then we will read it out loud, and we'll try to answer the question as best as we can. Okay. If you have trouble to really formulate your question at this time, you're always welcome to contact us after hours, of course, after the webinar is done. Just go to krusetraining.com and find our email address and send us an email with your questions. So that's definitely a possibility, okay? So don't hesitate, just get in touch with us, okay? So let's get started. Injection molding industry. It's a very complex industry. Yeah. So understanding the complex behaviors and interactions in the molding industry is really critical. If you, for example, are a part designer and trying to understand and optimize a part design, you really have to understand the polymer material that you are trying to design the part for, because otherwise you will not be able to optimize a complex geometry to make it fit and make it ready for the mold design. Yeah, that's very, very important. Understanding the critical components in injection molding is really, really, really important before you're trying to optimize a part design, because only if a part design is optimized, you really should go into the mold design. Yeah, if the mold designer needs to then do its magic to optimize the mold design, and when those two functions are basically done, then you can only then you should build the tool. And then when the processor gets the tool into the machine, it will probably have a very wide molding window. Okay, so let's take a look at some molded part requirements. What are molded part requirements? You really have to understand, before you even start designing a part, what are really the critical dimensions and tolerances. You need to also understand the part I'm going to design, the structural strengths and requirements. What does this part really have to withstand in use? Is it in an assembly? Is it a car bumper? Is it a syringe that will get used once and then thrown out? So what are really the structural strengths and requirements for the part you are designing? Appearance and aesthetics, of course. Is this a part that has a class A surface? So does it need to be very shiny? And does the end user really see this plastic part, or is it a plastic part that is under the hood in the car, somewhere tucked away, that is a structural part that you really don't care what it looks like? It's more important what the functionality is than what the actual appearance is. So these things are very, very important to understand prior. In addition, of course, you need to evaluate what are acceptable shrinkage and warpage behaviors in the part. For example, if you have an assembly of multiple plastic parts that have to be assembled at a later stage, then you have to really understand what is the warpage behavior of each individual part. And in the assembly, under certain circumstances, if you have an assembly, part warpage is okay. If all of the parts warp in the same manner, in the same behavior, then they maybe can be assembled without a problem. Okay, so the assembly functionality is really, really important to understand for an assembly, a molded part assembly. Okay. All right, so what's the Circle of Knowledge training program? Really, what's the Circle of Knowledge? What we're trying to do with that is we are trying to build a synergistic team of professionals. So each of the teams understand really the other team's tasks and challenges. So if a part designer would understand a little bit more about mold design and processing, he or she can design a much better part. And if the process engineer would understand how a mold is designed, the water lines are laid out, where are the ins and out, what's the mold steel, they can influence their process such that they can make a better part. So the interaction between those fashions is really, really important, okay? So that everybody speaks the same language. And that's the reason why we created Circle of Knowledge, because we believe if you know each other's business just a little bit longer, a little bit better, you can design parts much easier. So this training program is available online, of course, 24 hours, 7 days a week. We have very concise, focused learning lessons we have developed. At the moment, we actually have 87 lessons done, and I would say in the next 2 months we'll have another 9 to get us up to 96, almost 100 lessons online, available 24/7, 365 from any device, phone, tablet, computer, anywhere in the world. You can access this knowledge system, and we call it a knowledge system actually because what we're really trying to do is create a Wikipedia for injection molding. Yeah, so that you really can go in with your login and get the information you need, go through a lesson, and keep on working on your part design, mold design, or on your process. We actually have companies have this system on their tablets at the molding floor. When they have a molding defect they need to solve, they go through a lesson and say, now I remember, and go back to actually solving this molding defect. Okay. So let's go now and look at our webinar lesson, the Polymer Materials Overview. So give me just a second to pull this up. Here we go. I'm going to show you this, really how that works. So this is our website. Yeah, you can check this out in detail if you want. Polymer Materials Overview. Let's go.
It is important for part and mold designers not only to understand design principles, but also to understand the fundamentals of plastics. The choice of a plastic or polymer has a strong impact on the outcome of the molded part. In this lesson, we will review the basic structures of polymer materials. In this lesson, you will learn the different classifications of polymers and their key characteristics, the basics of polymer creation, including monomers, chain molecules, and side branches, internal bonding mechanisms, both primary and secondary forces, the microstructures of amorphous and semi-crystalline materials. Polymers are categorized by processing methods and temperature behavior. The major groups are thermoplastics, thermosets, and elastomers. There are also compounds made up of polymer blends, copolymers, composites, and thermoplastic elastomers. The most common are thermoplastics. These are polymers that melt by heating and solidify by cooling. Thermoset materials, generally rigid polymers, are injected at a low temperature and then cured with heat inside the mold. This creates an internal chemical reaction that forces the molecular chains to cross-link and form a solid molecular structure.
So again, this is very, very important to understand when you design a part or when you actually process a part. Most of us obviously are molding thermoplastic materials. Fewer of us do thermosets, bulk molding compounds, liquid silicone rubber, and rubber itself. So really the difference is that these molecules in a thermoplastic material are just chains, like almost like a bowl of spaghetti. A spaghetti in a bowl of spaghetti is a thermoplastic material. The molecular chains are just randomly distributed and are on its own, and they can be reheated. In a thermoset material, when a material is injected into the mold, and usually the mold is hot, so what will happen is these molecular chains, they really grab each other and create a chemical bond. This material is then thermoset. It is set. You cannot remelt this material. You can only destroy it. While as with a thermoplastic, as you know, we can regrind the part and we can reuse the material as recycling material as well. Okay?
The molecular chains create a chemical bond that cannot be remelted. Lastly, elastomers and LSR, liquid silicon rubbers, are elastic, but are also cured with heat and internal chemical reactions. For this lesson, we will cover the basics of how a polymer is created. Polymers can be made by polymerization, polycondensation, or polyaddition. In addition, rubber from natural materials can be vulcanized to create specialty compounds. The smallest building block of a polymer is called a monomer. Here you can see an ethylene monomer, which is used to create polyethylene by polymerization. Thousands or even hundreds of thousands of monomers are combined to build a monomeric molecular chain called a macromolecule. Molecular chains vary in length and shape, depending on the nature of the polymerization process. A homopolymer is material that has been polymerized using the same monomer, like PE, polyethylene, PP, polypropylene, PVC, polyvinyl chloride, or PS, polystyrene.
So
how do we determine the length of the molecules? Determining the molecular weight distribution, or the degree of polymerization, is one way. The most common technique for measuring molecular mass is a variant of high-pressure liquid chromatography, HPLC, known by the interchangeable terms of size exclusion chromatography, SEC, and gel permutation chromatography, GPC. In practical terms, higher molecular mass translates to longer chains. This creates more entanglements, which take longer to untangle, realign, and flow. Molecules need to be aligned for a material to flow easily through a runner, gate, and into a mold.
Yeah, that's very important to understand. So every thermoplastic material has reoccurring molecules. And they build a chain, and as longer the chain is, as more entanglement, as more difficult it is to heat up, as more difficult it is to align those molecules like spaghetti to be able to inject them into a mold. Okay, that's very, very important. Understanding this polymer material can help you solve processing questions.
Imagine that the molecular chains of a polymer are like logs floating down a river. If all the logs are aligned in the same direction, they can easily flow down the river. But if some of the logs turn sideways or transverse to the direction of the water flow, they create resistance, and the overall flow becomes much more challenging. The internal structure of amorphous materials is like strands of spaghetti in a bowl. A single strand of spaghetti has defined length, structure, and features. Even if the bowl of spaghetti is stirred, the characteristics of that one strand do not change. It's just in a different position within the bowl.
Very important to understand. if an amorphous material is heated up, like a polycarbonate, like a polystyrene, like an ABS, these are all amorphous materials. When you heat it up, you basically make the material to flow, and through the heat, these molecular chains are not changing, they are just randomly dispersed.
All the spaghetti in the bowl has a random coil conformation. Now that we've learned how polymers are made up of long chains, we will move on to the internal bonding mechanisms. When a macromolecular chain is created by polymerization, the atoms are joined by primary bonding forces. These strong forces hold the monomers together in the molecular chain.
Very important. A molecule, a monomer, is one little building block. It's almost like a brick in a house. And if you put another brick in the house in the same location, the cement you are going to use is the connection, and that's very strong. Okay? So there are primary bonds that are very difficult to destroy, only with overheating or with force.
In addition, there are secondary bonding forces present between the individual chains. Because these forces are about 100 times lower than the primary forces, they can be softened by applying heat, which lowers them further and allows the material or molecule chains to slide along each other to flow.
Very important. Between the molecule chains, these forces between these chains are very, very low in comparison to the atom forces or the connections between the individual monomers, excuse me. So it's almost like, if you think about, again, the bowl of spaghetti, the spaghetti, when you pull on it, or like a rubber band, it's kind of a strong, it's strong, the strength is there. You can't break it very easily. But in between the spaghettis, you have the tomato sauce, and tomato sauce, it's very easy to take apart. So that's the difference, between primary and secondary bonding forces. It's almost like a bowl of spaghetti with meat sauce, okay?
Note that this is true for thermoplastic materials, as we saw earlier in this lesson. Heat softens the material and allows it to flow, while cooling it reverses the process. Let's take a closer look at the structure of a molecular chain. Chains can be different lengths. It can also have various branching characteristics. Some chains have few branches, while some may have multiple branches of varying lengths. The number and length of these side branches will have an impact on the secondary bonding forces.
Okay, that is very important. You have molecule chains that don't have any side branching, and you have some that have side branching. Just think about low density polyethylene and high density polyethylene.
Materials with no side branches are denser, thus requiring more heat to loosen the secondary bond, allowing the material to flow. Materials with more and longer side branches are less dense, and therefore require less energy or heat to loosen the secondary bonds. These materials flow with less heat input. Within the category of thermoplastics, there are thousands of different base materials and grades. Although it's virtually impossible to fully understand every available material, having a solid understanding of basic polymer characteristics is imperative to successful part and mold design. Let's take a closer look at the thermoplastics group of polymers. This group is further broken down into two main categories, amorphous and semi-crystalline. We are only discussing thermoplastic materials in this section, since thermoset and elastomer materials are mainly amorphous, so will be discussed in later lessons. Amorphous materials have no directional properties. Although semi-crystalline materials also have some amorphous regions, they contain mostly crystallized areas. This may result in directional properties that could cause inconsistencies in part properties, in addition to shrinkage and warpage behaviors. All thermoplastic materials have an internal microstructure, or morphology. This microstructure affects the material's behavior during the molding process. Let's start by looking at the internal microstructure of an amorphous material. Amorphous materials have a random microstructure, meaning the molecular chains have no specific orientation or internal order, like the earlier bowl of spaghetti example. When the material is heated, the secondary bonds loosen and the material begins to flow. The heat must exceed the glass transition temperature, shown in this graph as Tg, after which the flowability improves with increased heat. As materials flow, their molecular chains align. When they stop flowing, the molecular chains return to their natural coil-type structures. When polymers go back to their natural relaxed molecular state, the molded part shows very little molded-in stress, and therefore less potential part warpage and higher dimensional stability. If the aligned molecules are frozen during flow, their alignment is maintained, resulting in flow-induced mold-in stress. In clear parts, this can be evaluated as birefringence.
So this has been a lot of information all at once here. So let's recap this just a little bit. Remember, when you have a material, if it's an amorphous or semi-crystalline material, you really need to know this because they do react to heat and cooling differently. So as a processor, make sure you get the material spec sheet and I evaluate what material am I going to process. Then secondly, when you heat the material, the secondary bonding forces loosen up. Yeah, it's almost like when we go to Florida, where I am, yeah, when it's a little warmer, we have a little bit more mobility. Okay, so, and then these molecules are made to flow. They are flowing, they're aligning themselves in the direction of flow. And as soon as we the material stops flowing, these molecules go back to a coil formation, we call this. They want to tangle up again. And if you freeze the material in while it's flowing, which we call flow-induced stresses, then there is a problem potentially. Yeah? With flow-induced stresses, the molecules don't want to be frozen in, aligned, and therefore you may have trouble with molded-in stress. Okay, so that's the basics of how materials work. You heat them up, the molecules align, they flow into the mold. When you pack it, they are coiling up again, they are compressed as higher the pressures are, and they are cooling in that state. Okay? Differences, amorphous and crystalline material react differently. Okay? Very, very important.
Amorphous materials have a wide process range and can be molded with fewer challenges, resulting in molded parts that are more dimensionally stable. Now let's move on to the internal microstructure of semi-crystalline materials. These materials do not fully crystallize. However, they have densely arranged molecular chains with few or no side branches. This structure allows the chains to embed themselves into the crystalline areas. So the areas that have not yet crystallized have an amorphous structure. Crystallization takes place above the glass transition temperature. When the temperature drops below this point, the molecular chains lose their ability to move, halting the formation of crystalline areas. Crystallization is only formed if the secondary binding forces are high. Otherwise, the material adopts a more random amorphous molecular structure.
This is very, very important. So there's two different structures, amorphous and crystalline. So just think about if you don't know which material you're molding, it probably will have an effect on how the quality of the part is. So please make sure to know what you're molding and to set up the process in accordance with the material you are molding, because the process will be different.
Generally, semi-crystalline materials have a higher inherent shrink rate, which is affected by the rate of cooling. If the melt and mold temperatures are low and the material reaches the glass transition temperature quickly, or in other words, has a fast cooling rate, the material cannot crystallize and will have lower shrinkages. On the other hand, if the melt and mold temperatures are higher and the cooling rate is slower, the material will have time to crystallize, which will result in higher shrinkages.
So that's very important for all of you that are known to mold semi-crystalline materials, for example, like a nylon material, polyamide. So what most people say to me is, I got to run a low mold temperature to keep my dimensions. So, well, when you do that, you run a low mold temperature. That means a fast cooling rate, and you have less shrinkage. That means the part is larger. What the problem here is because this crystallization does not happen, it will happen later on in the part after molding. It's called the after shrinkage. Yeah, the post-mold shrinkage, and that can deform the part. So isn't it better to run this semi-crystalline engineered material at the proper mold temperature, have a slower cooling rate, create more crystallization? Yes, you have more shrinkage, but you have a lot more stable part in use. It doesn't bend, doesn't deform, it will function more properly than if you run a low mold temperature on a semi-crystalline material like a nylon.
Semi-crystalline materials have a narrower material processing temperature range. These materials are opaque and have a good resistance to chemicals and lower moisture absorption. However, they have higher shrinkage rates. This is important for process technicians to understand when molding semi-crystalline materials. This concludes Section 2, Lesson 1, Polymer Materials Overview. In this lesson, you have learned the different classifications of polymers and their key characteristics, the basics of polymer creation, including monomers, chain molecules, and side branches, internal bonding mechanisms, both primary and secondary forces, the microstructures of amorphous and semi-crystalline materials.
This is the quintessence of what you need to know to be able to correctly process these type of materials. Thermoplastics we talked about, thermoset we talked about, but more so because most of us are really using thermoplastics. It is really important that you know at least which material it is, if it's an amorphous material, if it's a semi-crystalline material, and how to properly process this material. Okay, that is the key to be successful in processing and designing, of course.
As we saw in this lesson, there is a vast array of polymer materials available, from modified natural materials to thermoplastics, thermosets, and elastomers. In addition to these base materials, there are thousands of derivatives enhancing and changing the properties of the materials. Although it would be almost impossible to understand every option, having a general understanding of the basic properties and structures of polymers will help part and mold designers, as well as processors, make choices and decisions that will optimize the final part.
Okay, so that was the initial presentation of the material. Let me go just one step in here and say, okay, let's conclude. What we're trying to do in the Circle of Knowledge training program is really combine the part designer, the mold designer, and the processor, just so they understand each other's business just a little bit better. And the material, as we just saw, is a major factor in that. The material should influence how the part design is optimized. The material should be influenced as well how the mold is designed, because different polymer materials have different cooling characteristics as well. So you can modify and optimize a mold design to the material to be effective, to run a very fast cycle. And the processor, of course, that has to make this happen at the machine, he really needs to know materials as well as the part design and the mold design to make it happen to mold a quality part. Okay, so that was concluding our webinar for today. Again, I can see that there are not many questions coming in. So what I would suggest is please take a moment, go to the Kruse training website. If you like to ask a question, don't hesitate. Underneath here is my email, Torsten_Kruse@krusetraining.com. You're always welcome to send a note there. I will be responsible and to get the answers you need. Again, thank you very much. I hope to see you next week for another webinar. And again, don't hesitate to contact me. I'm here to help. Thank you.